Hello class. In lesson 4.2 arcs and circular motion, you'll learn to find the arc length of a circle, find the area of a sector, and then find the angular speed and linear speed using again some of this formula stuff here. So let's begin by first going over what the arc length is. The arc length is the distance of an arc, which is this right here. This is referred to as an arc. And S is the symbol that we represent to measure the length of the arc. R is obviously your radius, where this right here is R, which stands for radius, and theta represents the angle. Now, to figure out the measurement, the distance of this arc here, we simply multiply. The formula is that S, the arc, equals to theta times the radius. That's all we have to do. Simply multiply the angle by the radius times radius. The only catch is that the angle has to be measured in radians. It has to be in radian measurements and not degree measurements. So for example, to figure out the arc of this, to figure out the length of this arc here, S is going to equal to theta times R. And here theta is 3 pi over 2 times 60. Which 3 over 2 times 16, that equals to 24. So we end up with 24 pi. I want to keep my answer in terms of pi right now, okay? So we end up with that. And if we want to estimate what that value is, we simply add the pi in there. Which I mean I'm multiplying by pi. So 24 times pi, that's approximately 75.39. What's the unit measurement here? Feet. So feet. So approximately that many feet. So again, to figure out the arc length, remember first of all, I need the angle theta to be in radians. So the first thing I'm going to do is convert this into radians by multiplying by pi over 180. That's 60 pi over 180. Which reduces to 1/3, so 1/3 pi. And R, which is equal to half the diameter, would be half of 36, which is 18. So the arc length here would multiply those two things. Which is 6 pi. And 6 pi is approximately 6 times pi, 18.85. Whatever units measurement this is. Okay, and because it's a length, again, it's a linear unit, all right? So not squared, it's to the first power. All right, and that's how you calculate arc length. Now, moving on to the area of a sector. To get the area of a sector, well, first of all, sector again is the inside part of an arc. So again, this is my arc. So the area would be all of this. That would be the area. Again, R is our radius, theta is the measurement of the angle, and we're looking now for A, again, for the area of this sector. Well, because we're doing a different value, looking for basically the number of squares inside there, the formula is obviously going to be different. The way we calculate area of a sector is by multiplying half times the angle times the radius squared. And again, the only catch here is that our angle theta has to be in radians, not degrees. It has to be in radians. So let's look at an example of this. Let's find the area of a sector with a central angle of 240 degrees and a diameter of 8. So we have a central angle theta that's 240 degrees. We need to first convert that into radians. So we're going to multiply by a conversion of pi over 180. That gives us 240 pi over 180, which we can reduce by dividing by 10 and by 4? No, 3. So 8 pi over 6. Oh, we could simplify by 6. What am I thinking? Let's simplify by 6. So 4 pi over 3. So this reduces to 4 pi over 3, and our radius is half our diameter. And since our diameter is 8, half of 8 is 4. So we're going to get our area by multiplying half times 4 pi over 3 times 4 to the second power. And let's see what we get. So half times 4 over 3 times 4 to the second power. Let's convert that into a fraction, and that's going to give us a total of 32 pi over 3. Let's see, let's multiply it with pi so we can approximate that answer. And when I actually multiply it with pi, that approximately is 33.51. And this one, because it's area, it's going to be square units, so square feet. And that is your area. Let's do another example. So here, again, well, we have the angle, the central angle is already in radians, so that's 17 pi over 12. I'm forgetting the rest of the formula. 1/2 times the central angle times the radius squared, which is 1/2 times 17 pi over 12 times the radius of 14 squared. So 1/2 times 17 over 12 and then times 14 squared. That's going to give us a total of 833 pi over 6. That's the exact value. Now the estimated value simply multiplies again this fraction with pi. So let's multiply our answer with pi and let's see what that estimates to. And there it is. Approximately 436.16. And there's your answer. Again, square units. With the units here, yards, so square yards. There's your answer. Okay, this is your exact answer, and this is your approximated answer. On your assignment, I want everything exactly, okay? I want everything in terms of pi. So even though I'm estimating again in our notes, on your assignment, you're going to write everything the exact answer. So in terms of pi. All right. Now let's discuss circular motion. Now using again the fact that we have a central angle changing along the path, this is referred to as circular motion. So again, figuring out how fast an angle, so we're going around, figuring out the fast the angle theta is changing along a circle again that's moving around. Now the way that we calculate this, we use, first of all, this symbol right here. This one's called omega. That's the symbol that we normally use when discussing, again, angular speed. Omega here equals to our theta, our central angle, theta, divided by time. Now our time is equal to the revolutions per minute. I'm sorry, our minutes per revolution. So dividing by minutes per revolution means that this is equivalent to getting theta and multiplying it by the reciprocal of this, by multiplying it by 1 over t. And by multiplying by 1 over t, that means we're multiplying by revolutions per minute. Which I'm going to denote as RPMs. So the way we're going to get our omega here, our angular speed, is simply getting our central angle and multiplying it by how many RPMs there are. And the cool thing about this is that our central angle, because we're making a complete circle here, our central angle is going to be 2 pi radians. Because again, 360 degrees in terms of radians is going to be 2 pi. So for example, let's look at this example right here. Let's say a bicycle rotates with a radius of 14 inches, rotated at a rate of 125 revolutions per minute. So we have this tire again in the shape of a circle, and it's rotating again at 135 revs per minute. So it makes again 125 of these rotations in 60 seconds, in 1 minute. Well, our central angle, because again it's rotating 360 degrees, is, in terms of radians, is 2 pi radians. So the way we're going to figure out omega is by multiplying 2 pi with our RPMs. So 125. So omega here is going to equal 2 times 125, which is 250 pi radians per minute, which when I multiply that answer with pi and not write it in terms of pi, that's approximately 785.4 radians per minute. So that's how fast the angle inside here again is moving. So the theta, the central angle here, is moving 785.4 radians per minute. Now, if I want to figure out what that is in degrees, I just simply convert it into degrees. But we're going to keep our answers again in radians per minute. So there's your result. Now, to figure out circular motion, to figure out now what's called the linear speed, the distance again, that the outside parts, again, not the inside, not the angle, but the outside part of the circle is moving. Right, like if I had a tire and I put a point right there as an tire, how fast is this point moving around this tire? That is called linear speed. And the way we figure that out is by using the variable v. And what we do is divide our arc length divided by time. Well, arc length is S, right? And multiplying by time, remember, just like last time, is the same, I'm sorry, dividing by time, because time is measured in minutes per revolution. is the same thing as multiplying by the reciprocal, by 1 over t, which is then going to be revs per minute. So again, RPMs. And well, we know how to calculate arc length. Arc length is calculated by multiplying the angle with the radius. So substituting in S for theta times r, we get that the way we calculate our linear speed is by multiplying these three things: the arc length times the RPMs. So let's look at an example of this. So again, let's say we have the same tire and it's rotating again at 135 revolutions per minute. So in 60 seconds, this tire is going to turn 125 times. And what we're going to do is figure out, okay, if I put a point right here, how fast is this point moving around this tire? And it's not going to be the same, okay? It has a different type of speed. So the way we're going to calculate this, V, is by multiplying again our central angle times our radius times our RPMs. Well, if you look at this again and I rearrange this formula, rearrange the variables in this formula, and put theta with RPMs, our central angle with RPMs, well, we've done this before. We just did this in the last example. This equals to omega, our angular speed. So we can figure out our linear speed by simply multiplying theta with omega, which we know from the previous answer. Our radius here is 14, and we know that the value of omega from our previous answer, we're going to do it in terms of pi right now, is 250 pi. So multiply this by 250 pi, we get that the linear speed would be 14 times 250, which in terms of pi is 3,500 pi. And let's approximate this value. So let's multiply this number with the actual value of pi. And this approximates to 10,995.57. And the units is not going to be, again, radians, but it's going to be inches per minute. So inches per minute. And that's how we calculate, again, our answer, by simply multiplying our angular speed simply with the radius to get the linear speed, V. And because of this, then our formula to figure out linear speed using angular speed becomes this. We can figure out V, the value of V, equals to our radius times omega, which is simply our radius times theta times the RPMs. So that's all we have to do to figure out V, where theta has to be in radians, and theta is always going to be 2 pi radians every single time. So let's look at this example right here. So a ceiling fan with 25-inch blades rotates 40 RPMs. Let's find the linear speed of the tips of the blade in feet per second. So again, our velocity is equal to the radius times omega, which is theta times RPMs. So our answer here would be a radius of 25 inches times our central angle of 2 pi times our RPMs of 40. So 25 times 2 times 40, that equals to 200 pi And because the 25 is in inches, it's going to be inches per minute, because our RPMs, remember our RPMs, this is measured in minutes. So 20 inches per minute. Now we want our answer in feet per second, so we just have to do some little conversions here. So let's write in our answers of 200 pi over inches for every 1 minute. So let's convert this. Well, first of all, we want to convert the inches into feet. So let's do that conversion first. So we want to change the inches into feet. So I'm going to put feet up there, inches down there. And well, there's 12 inches in 1 foot. That cancels out that. And we now have our unit measurement in feet. I also want to change our minutes into seconds. So I want seconds in the bottom, and I want to get rid of minutes. So I'm going to put minutes on top, and that's going to reduce out the minutes. And because 1 minute has 60 seconds, I'm going to put 1 over 60. So here, to figure this out, I'm going to multiply these numbers over here, multiply these numbers down there, and then simplify. So we have 200 pi divided by 1 times 12 times 60, and the bottom is 720. Again, this is now in feet. This is now in seconds. I'm just going to simplify this. So our our linear speed is 200 pi, which I'm not going to do the pi right now, divided by 720. Let's convert that into a fraction. And that's 5 pi over 18. So 5 pi over 18 feet per second. And let's approximate this. So let's now multiply this answer with pi, and let's see what we get as a result. So we get 0.87 feet per second. So that's the approximated answer in feet per second. Let's do another example. So Ryan is riding a bike whose wheels are 28 inches in diameter. If the wheels rotate 130 RPMs, at 130 RPMs, find the linear speed in miles per hour in which he is traveling. So again, the linear speed V equals to our radius times omega, which is R times theta times RPMs. So the radius is not 28, so that's the diameter. So our radius is half of that, which is 14. Our central angle is always going to be 2 pi, and our RPMs is 130. So 14 times 2 times 130. That's equal to 3,640 inches, because that's what our radius is in terms of inches per minute. So inches per minute, because again, it's RPMs. Now we want to change this into miles per hour. So we want to change the conversion into miles per hour. So let's see how many miles per hour that is. Oh, I forgot the pi here. So 3640 pi inches for every 1 minute per minute. So every 1 minute. So let's convert this. We want to first convert the minutes into hours or the inches into miles. Well, let's see here. Let's do the inches into miles. Okay. Well, first, let's do inches. 12 inches make 1 foot. And there are 5,280 feet in 1 mile. Okay. So with that, I can get rid of the inches. The inches cancel each other out. Now the feet cancel each other out. And now my answer is in miles. So the unit is now converted into miles. Now I want to also change the minute into hours. Well, minutes, change it into hours. Well, 60 minutes in 1 hour. And that will reduce the minutes, and now I have my conversion. So here I would multiply all the top. So this times 1 times 1 times 60. Again, I'm doing it in terms of pi, so I'm not putting in the pi. So I'm just doing 3640 times 60. That's 218,400 pi. Divide this by 1 times 12 times 5,280 times 1. That's 63,360. And my units are, remember, in miles and hours. So that's my answer. So V is equal to 1. Well, let's divide those two things out. Let's simplify this, okay? So let's see. We have 218,400. Let's divide that by 63,360. Let's convert that into a fraction. So that converts to 455 pi over 132 miles per hour, which when we multiply by pi, let's see what that is. So let's get this answer, multiply it with pi. That's approximately 10.83 miles per hour. Okay, and there you have it. So that's how you figure out your your linear speed using your angular speed. And there you have it. Okay. All right. So that concludes again the examples on this lesson on using on finding linear speed, angular speed, arc area, and the arc length. Well, again, like always, I appreciate you watching. If you have any questions, please send me a message through email or remind, and I hope you have a great day.